Gibbon from Imperial College, so not too hard.
Yes.
He's talking to us about vorticity in 3D Navier-Stokes equations, so thank you very much.
Okay, thank you Beatrice and Mike for the invitation. I'm aware that this is a PDE meeting, but it's also a GFD meeting, and probably most people are not too interested in Navier-Stokes per se, although of course the Navier-Stokes equations are the basis of many GFD models. However, this isn't really going to be a function space Navier-Stokes talk. It's more of a numerical one, or half numerical one, and it's really done in collaboration with 5 other people. And instead of telling you the story now about who did what and why and how, I'm going to tell the story, as it were, as to how we got into this and how I met these people, and that will sort of come out during the talk. But just specifically, Diego Donzis from Texas A&M, Robert Kerr, who would be familiar to most of you in Warwick, Rahul Pandit of the Indian Institute of Science, and his student Anupam Gupta, who's now in Rome, and Dario Vicenzi from Uriel Frisch's stable in Nice. And so they're all involved in this material. Okay, so just to give you a little background. Okay, let's write down the familiar Navier-Stokes equations with some sort of specified forcing, which is sort of L2 bounded, etc., etc. And we're going to be on the usual periodic domain. Now, my motivation for getting into this, and this is how I want to tell the narrative, my own motivation was the following. I've been interested for many years in looking at how an analysis of intermittency will tell us something about Navier-Stokes and its regularity properties. That's where I was coming from. Okay. Now, what is intermittency? Well, normally we would think of intermittency as violent, local, spiky surges away from averages, with possibly long time scales in between, so it doesn't violate averages. And that would that's normally observed to happen in the vorticity and the strain field. For instance, if I go over, this is a plot from a friend of mine, Christos Vasilikos, in aeronautics at Imperial, and it's from a wind tunnel, and it's the longitudinal velocity derivative at a single point. Okay, and essentially what you're seeing is an extremely spiky spectrum, and this is about Reynolds lambda 200. So it's a turbulent flow, but it's not that turbulent, and it's very spiky. And basically, when you look at the spectra of all these things, either in space or time, this is a typical sort of picture. And another typical picture would be every respectable turbulence group has some cube picture like this. I borrowed mine thanks to Mark Taylor and Darrell Home. This is the big Los Alamos 248 cube simulation, and you take a typical cube, this is a subcube here, and what you're seeing are contours of the vorticity field, and you're seeing an extremely heavy clustering of the vorticity field, and if you did it for strain it would be the same but different. And it's essentially telling you that if you're sitting in a box like this and you're in like a turbulent sea, the sea is not Gaussian at all. It's actually heavily clustered. And if I go back, the first people to really observe this was Batchelor in Townsend in 1949. If you go back and read their paper, it's somewhat of a classic, because they really said, well, you know, everybody thinks then, pre-war fluid dynamics, that really turbulence was a Gaussian flow. And if you think of what's called the flatness, which is the 4th order moment over the 2nd order moment squared, which is a typical signal processing thing that you would look at, for a Gaussian flow that would be 3, except they were finding measurements that went up to almost 6. And that then, at that time, was a surprise. And essentially the reason is because of the clustering type of phenomenon that I've shown in the previous pictures. And there's been a whole you know, if you go through the books like Frisch's book, the papers by Srinivasan and Menon-Vo, there's a whole generation of literature since 1950 on this sort of thing. And this Ishihara Goto Kaneda review is also very good. Now, when you look at, say, the flatness in a wind tunnel flow, 5 point something, the foreign exchange market, which is going through millions of transactions a second, there's $4-5 trillion a day circulating around the planet through the forex markets. The signals in that are, well, about 5 years ago they were like 12. They're probably by now, they're probably like 15 or 18. And in the atmospheric boundary layer, the flatness gets up to more than 40. So you're talking, this is real turbulence. Okay, so let's move on. That was my motivation. Now the problem with this is what sort of variables do we pick to get into the problem? Okay, now at the bottom of this slide, typically in the physics and engineering community, people look at statistically stationary flows and they use anomalous scaling functions. Typically, of course, you say, let's sit at a point x, take a radius r around it, and then take the difference in the velocity field here to the pth power, and then you ensemble average it. And then in Kolmogorov's language, this scales like r to the zeta p. And this zeta p, in Kolmogorov's language, it would be linear in Kolmogorov's theory, except observationally, numerically, it's actually a concave curve below linear. It's exact for p is 3, but thereafter it's a concave curve below linear. And therefore, because it doesn't go as Kolmogorov's theory says it should, they call it anomalous scaling. Now, these structure functions, as they're called, are all very nice for statistics, but for a PDE, they're impossible. I'm not saying it's not possible, because another generation might be able to construct some analysis that can use these, but it's extremely difficult for a PDE to do anything with structure functions like that. And therefore, I mean, one thing, anybody who's dealt with Navier-Stokes, what on earth do you do with the pressure field? It's really extremely difficult. Therefore, my motivation was to say, well, for PDEs, what we really ought to use instead is much higher LP norms of the vorticity field. Okay, now we're familiar with L2, where M is 1, because of course that's the global entropy. Okay, and we're familiar with M is infinity, because that's the L infinity, the subnorm. And now, of course, you've got a whole range from M is 1 up to M equals infinity in between. And so, taking out the volume here, okay, essentially, by Holder's inequality, these guys must, as long as there is a solution, these guys must actually always be ordered in that manner, whatever the solution is. Now, one hits upon a rather unusual scaling in the following way. First of all, I'll do this backwards. First of all, there is a scaling property that if you scale everything with an epsilon, but not L itself, you come up for the omega m's with this strange scaling, this alpha m, which is 2m over 4m minus 3. And you note that when m is 1, alpha 1 is 2, and then it goes down, it decreases down to m equals a half. Now, I'm going to first of all take out the dimensions by putting this omega naught to the minus 1. So that's like the frequency of the box. Okay, so you non-dimensionalize it and then raise this to the power alpha m. I'm going to call these dm's. Now, it turns out that there are estimates on the time average, long time averages of these things for all m is 1 to infinity. And then, having had that as motivation, I'm going to describe 4 numerical experiments plotting these d's, because we thought they were sort of interesting, that the system was telling us something. So that's where partly my motivation came from. Okay, so I'm repeating that information at the top of the slide, the definition. This symbol here is a time average up to time t. Now note that whereas the omegas must always be bounded as long as a solution, of course we don't know as long as a solution lasts, because if it doesn't last then the omega m's will go to infinity, but as long as there is a solution that must always hold. But the ordering for the d's does not necessarily hold, because the alphas are decreasing, the omegas are increasing. So if, for instance, omega 1 and omega 2 were extremely close, the exponent on omega 1 is bigger than the exponent on omega 2, so they could flip ordering. So you can't assume that the d's are ordered in the same way as the omegas. That's very important. Okay, now there is a result, a neat result by myself. The weak solutions that force Navier-Stokes, they're all bounded from m is 1 to infinity by either Grashof squared or Reynolds cubed, depending on which you want to use. Now this is really based on a result. This result was forgotten about for many years. There is a time average result. If you take n gradients, the velocity field, and if you take it over 2m minus 1, Foyash Geopre Timam, whoops, can't spell Cyprian's name, Colette Geopre and Roger Timam, 1981. They basically, now there is a constant there which isn't dimensionless, Reynolds cubed. And this is true for weak solutions. Why it's true, you have to go through all the stuff to prove it. But assuming this result here, it's very easy to actually then prove that the time averages of these d's is bounded by this, and this constant is dimension-free and uniform. Okay. Actually, the way it comes up is that you take your omegas, you put some arbitrary power on them, you work it through, and then you say, well, using that result there, what are these parameters up here? And they immediately come out as these alphas. Okay, so the symmetry scaling is really sort of working its way into the analysis. Okay, now having got this result in 2011, I said to myself, well, it would be nice to compute these things. But before I show you these results, let me just point out, if we take m is 1, we are back to the standard time average of the dissipation, which has to be bounded, which has been well known. It's bounded by Reynolds cube. When you turn that into the Kolmogorov length, and this result really for m is 1 comes from Doring and Foyash, then it basically tells you that the length scale that you get from the time average dissipation is none other than Reynolds to the 3/4, which is the Kolmogorov length. So in other words, you've sort of hit all the right buttons with classical fluid dynamics and got a nice correspondence. So the bottom result, the lowest rung on this one, sort of like I say, hits what we know and love. Okay. So I keep walking to this machine thinking I have to change the slide, forgetting this high technology works in this. Okay, here we go. So let's do one more slide of mathematics. Let's take a look at these d's. As I say, these decrease, whereas the omegas increase, so there is not necessarily the same ordering in the d's as there is in the omegas. So we could say, right, well, there could be two different regimes, where the m plus 1s are less than the m's, or vice versa. And I'll call this regime 1, the blue, and this regime 2. Okay. Now, the question is, do the numerics give either of these, or is there a mixture? We'll see. But before I do, there is one result we can write down. I'm cheating a little here. If there is a solution, in other words, this is a formal result, although you can rigorously get out of this if you need to, you can find a differential equality on the D's with a fair bit of work. It basically comes out like this. This is the unforced version. If you want forcing, there's just one added term here. Of course, here is in effect like the viscosity, and here is the nonlinear term, but they've both got a dm cubed sitting. So then the question is, you say to yourself, well, if the dm plus 1s are bigger than the d's, or even just one of them, for just one m alone, that's all you would need. Because if you control any one d, any LP, you've controlled L2, and then you're, in terms of regularity, you're home. So the question is, can one numerically see whether any one d m plus 1 is greater than any dm? And I said to myself, well, surely this will be a very nice test, and maybe something will come out. And so I put the questions like this: regime 1 or regime 2. We ask the question, are either of these regimes favoured? Are the DMs well separated? If either of them are favoured, is there an oscillation? Are you in regime 1 for a period? Does it then flip and flip back again? A very obvious question. As for these processes, are they M-dependent, Reynolds number dependent, initial condition dependent, etc.? The standard questions you would like to know. Okay. And particularly the role of the bottom rung, the entropy D1. And so what we're now going to do is say, right, we have 4 numerical experiments. This came out very recently in Journal of Fluid Dynamics and with my collaborators. Now the story is that I asked Bob Kerr, I said, Bob, you have a new Navier-Stokes code. Can you run out these Ds for me? And he said, well, yes, I can. And at a meeting in 2012 in Dublin, he showed one slide of our results. Pandit was there and phoned his student Gupta and said, can you run out those results also? And he came back the next day and said, yes, we see the same thing. Okay, now Donzis was there. Now, Diego Donzis has possibly the biggest Navier-Stokes code in the world, or at least joint biggest. It's a 4096 cubed calculation on 100,000 processors. He was at this meeting, and we approached him and said, can you run these Ds out from your data? And he came back the same evening, can you believe it, the same evening, and said, yes, we see the same thing. And so we all got together and agreed that we'd pool our resources and do a sort of joint collaboration. And Vincenzi was also at Bangalore at the time, and he was supervising Gupta. And so essentially now what I'm going to do is tell you the story of their calculations and what they got. Okay? And I'll have to shoot through this fairly quickly because of time. So this is Bob Kerr's calculation, and he has a very long anti-parallel initial condition. So it's a pseudo-spectral code, unforced, so it's decaying. It's like a 2 by 8 by 2 times 2 pi domain. So it's a very long anti-parallel initial condition. What you're seeing here is a first reconnection at t is 16, you see here, a second reconnection at t is 96, and a third reconnection at t is 256. So you would imagine that you've got a very highly developed turbulent flow, particularly somewhere between here and here. Okay, so before I talk about these plots here, just to labour that point, for those of you who are numerical guys and you understand these things, you have to convince yourself that you really are in fully developed turbulence. I think this goes back to Orsag and Patterson, that essentially the velocity derivative skewness, which is this object here, minus SU, they called it, ought to lie between about 0.5 and 0.7 if you're in a this is a numerical experience, if you're in a fully developed turbulent regime. And you can see here with the red code, SU, that you're exactly down between here and here. You're actually in that region. Okay, so now here are the plots of the Ds. And you see from M is 2, D1 is so big, this is a log scale, D1 is so big it's off the top, so it's not actually put on. And so you see D2, D3, all the way down, if you can manage to extract enough data, and that's not easy, down to D is infinity. And although it doesn't really quite look like it, they actually do not overlap. We checked all the data and they don't overlap. Okay, so what you've actually got is an ordering. Now, when Bob sent me this by email, I said, wonderful, we have it, look at the ordering. They all order beautifully, and then after 10 seconds I said, but they're the wrong way round. I was hoping, one always hopes, I was hoping, well, all the DM plus ones would be bigger than the DMs, and that therefore the dissipation term in Navier-Stokes would win out, and we would have control. And I looked at it, and it's the other way round. And I thought, well, I'm a scientist. It's not given me what I wanted, but it's something interesting. So let's take a look at it. Okay. And so actually what Bob was able to do was extract statistics for M is 1 to 9, but he couldn't go any further. Because it's not, for M is 3 onwards, it's not an easy task. You've got to be very careful. And he said he couldn't trust his data beyond 9. And D infinity is sort of an approximate trying to find the subnorm on a grid and testing where you think you have a maximum. Okay, right, and this is a 512 times 2000. It's really 1024 because there's a symmetry, times 2048 times 1024. And his Reynolds number is probably, I think, probably in the region of about, Reynolds lambda about 400, something like that. So it's a big calculation. Okay. So having established this ordering in the Ds, which surprised us, okay, let's now go to the Texas A&M data set. And this is forced stationary isotropic turbulence. And there's two forms of forcing. Now, this Texas A&M database is enormous. It's 4,096. The emerging Reynolds lambda is 1,000, so it's enormous. Okay, and it's done on roughly 100,000 processors. So I think along with Canada's calculation, it's the joint biggest Navier-Stokes calculation that there exists. And it's basically reported in these papers, Donzis, Young, Srinivasan, etc. These 3-4 papers is basically based on this code. Okay, and we needn't go into the detail, but there are two types of forcing, deterministic and stochastic. So what is basically written as EP and what is FEK in the next slides are essentially these two different types of forcing. Okay, now these are the omegas, and this is forced statistically stationary turbulence, so it's versus Reynolds lambda, and you can see the omegas, and of course they have to be separated because Holder's inequality says they must. But this is at least a good test of the code in the sense that it shows indeed that they are. And you see the triangles, the different circles, squares, are all dependent. Open and closed symbols respond to the two different types of forcing. Okay. So what do the Ds look like? Well, here are the Ds. They too, you see, they too are essentially ordered. Now these are so much together, M, and you see also dm is greater than dm plus 1, it's going downwards as before, and this is this blown up, it's sort of zoomed in. Okay, so you're seeing exactly the same ordering on the Ds as we had in the previous calculation. Okay, now here are dm plus 1 over dm, so it has to be less than 1 according to the previous slide, which it is, and they seem to be squeezing together as the m goes down. Okay, now we come to the third pair of calculations. And these are the Bangalore-Nice calculations. Okay. This is a decaying calculation. It's a pseudospectral method. Now, whereas Bob's was pseudospectral on a elongated domain, this is a cubical domain. And you're seeing exactly the same. D2, D1 is way off the top. You're seeing D2, D3, exactly the same, coming all the way down. They are actually separated. The guys did a very careful analysis of their data to be sure they didn't cross over anywhere. Okay. Like I say, this is a log scale, and D1 is off the top. So there is like a severe drop, and we'll come to that point later on at the end, if I can get there. And then this is their stochastically forced case. Now, this is a little technical as to how you force this particular problem, but they've taken a forcing of this type. I'm told by those in the know that this is a fairly standard method. And what it does, if you get the thing right, it maintains a constant Grashof number, which in this case is like 5 times 10 to the 7th. And what you're seeing is precisely the same. Because this is forced, of course, these sort of reach a plateau, but you're seeing precisely the same ordering as you go down. And strangely enough, if you look at the DMs averaged versus the Grashof number on this, because this is a different scale than this is exactly the Grashof squared or Reynolds cubed bound that we had earlier in my theorem. So you're almost, so actually there is m is 1, so there is actually the Doring-Foyash time average of D1 bounded by Grashof squared or Reynolds cubed, and you're almost actually saturated. So again, that's a sort of nice test. So those have established something interesting, I think. Certainly the dm plus 1s is always less than dm. The question now is there is a severe drop from D1. What does it actually tell us about D1? So the guys did the following. Since it's a log scale, I asked them to plot from there. So this is Kerr's, and these are the two Bangalore calculations. Basically plot log dm versus log d1. And what you're seeing, it's not a very good picture, I'm afraid, but that is 0.5. This is like 0.43 maximum. This is 0.42. So what you're seeing is that log dm multiplied by some coefficient log d1, that the AMs are always less than a half. We could actually say so slightly less than a half, but basically less than a half, which is telling you that actually the DMs are less than D1 to that power, which is less than a half. And what that's telling you is actually you've got depletion of nonlinearity in the system. Because it isn't just, when I was saying, well, they actually, D1, D2, D3 going down like that, that's sort of like linear, but it's actually better than linear. Basically, it's going down like this half power. And so, I'm actually got plenty of time left. So, just to summarize, this was regime 1, this was regime 2, which we never saw. There was never any evidence of a jump over, even over some small time, that always was separated, so we never saw any evidence of jumping into regime 2. Okay, now just to observe, to do a check, here is dm plus 1 less than dm. There's that alpha m plus 1 power over on there. And we know by Holder's inequality that this is true on the left. So as we start to increase m, alpha m over alpha m plus 1 comes down to unity, okay, and this is unity on the lower bound. So in other words, it's telling you that alpha m plus 1 of alpha m is being squeezed down to 1 as m is increased. And if you do the same calculation, simple observation for the d's, you find the d's, m plus 1 over m, are being squeezed up to 1 as m increases. And that's, if I could just go back, you see that's exactly what you're seeing. That you're seeing these things being, in all the calculations, they're being squeezed, the higher m's, they're being squeezed down together. So this is simply consistent with the numerics. So now let's look at depletion of nonlinearity and go back to my differential, slightly illegal differential inequality for the d's. Now this is dm cubed, so I could rewrite dm cubed as dm d1 to the 2am by inserting my numerical observation. So this is a mixture of analysis and numerical observation. Okay, so basically that would be this term, and this term times dm, you can actually easily prove, just analytically, it's simple algebra, that this is always greater than 1. When I saw that, I thought, oh, that's interesting. And then I realized, essentially, this is a different version of Poincaré's inequality. So essentially, it gives you the linear term on the negative part. But essentially, it says that this is minus linear in dm, and that this one, in effect, is dm times d1, because we've observed that 2am is always less than 1. So I'll just write that as a half for simplicity. Now, of course, that's then linear in dm, and I can integrate it trivially. And so it's telling me that the dm's now have an exponential bound, which is negative in t, and then the integral of d1. But of course, that integral of d1 is Lerais inequality, and it's always bounded. And therefore, essentially, my dm's are always bounded. It's not a very good bound. It's an exponentially growing in time bound, but it is bounded. And so Navier-Stokes solutions are regular in this region. And so, like I say, I think we can work on this and do better than this. In fact, I can do better than this, and we are working on it, but it's not enough time to tell you. But essentially, what we're concluding is that this regime 1 that we've observed in these numerics actually is a regular regime in terms of Navier-Stokes. Okay, so what is our conclusion? I'm going to finish a little early, but I'm sure people won't object. Okay, let's look at our conclusion. We ask the question, is this ordering observed in the DM, is it a valid tool to understand Navier-Stokes solutions? Clearly the idea needs more testing. I mean, we've got four, actually 5, because there were 2 forcings of Donzis, there were 2 types of forcing in Bangalore, and Bob's was a decaying calculation, so there's really 5. But nevertheless, the idea would need more testing in a wider range of initial conditions. Could we cook up initial conditions for which regime 2 is the initial condition, the other way around from what we're observing? Well, I asked Bob to look at this, and I'm sure he won't mind me mentioning, he did, with his code, a big Euler calculation, and really sort of sweated it to the limit it would go, and he said that for Euler, the D's crossed. Okay, so then what he did, he switched off the calculation, kept that as an initial condition, switched on the calculation with viscosity, so it then became a Navier-Stokes, and so he therefore had that regime 2 as his initial condition for Navier-Stokes, and ran it as a Navier-Stokes calculation, and he said immediately it switched back, almost instantly. So the answer is yes. In one case, we have cooked up initial data for which this is true, and it did indeed switch. So clearly, this ordering of DM, that regime 1, seems to be, as far as we can see, a property of Navier-Stokes. Okay. So then the question is, do other variations of Navier-Stokes share this property? What about buoyancy and rotation, which GFDers are always interested in? And the answer to that is that Beth Wingate at Los Alamos, although now she's in Exeter and going to arrive tomorrow, And Jared Whitehead, her postdoc, did a calculation on the Los Alamos machine and discovered that essentially on their code, the same ordering of the Ds as I'm reporting to you holds, and that they had buoyancy and rotation in their code, and it didn't make any change. You still have the same ordering. Okay. And then what about other models? For instance, non-hydrostatic primitive, in effect, is Navier-Stokes with bells and whistles. But what about the hydrostatic primitive equations, which Idris and his student Sao proved are actually regular in 2010? But despite the fact that they are regular, one wonders, does this regime 1 ordering actually hold for those? Or would it hold, for instance, compressible Navier-Stokes? The answer to those is I don't know. But if some of them actually went to regime 2, it might be some way of telling you how close one's model actually is to Navier-Stokes or not. It might be one way of doing that. And 6 minutes early, I've finished. Thank you.
About the initial conditions which you can cook up.
Yeah.
I mean, can't you just write some down?
Well, yes, but when you actually look at it, it's not that easy, because if you want dm plus 1, what you have to have is data for which the omegas are very well separated. So if you've got, say, omega 2 here and omega 1 there, when I raise the lower one to a bigger power, they don't flip over. And actually, you've got to have very, very spiky data, extremely spiky data, to actually get the omegas sufficiently separated, which I think is what Bob had in his Euler calculation. He went really to the limits of his Euler calculation when it was already beginning to grow extremely high into a very high spike, and then they flipped over. So it's not so simple. So I don't think the ordering in itself is that exciting, but at the same time, I think the fact that the ordering is sufficiently stretched below D1 that it's giving you this depletion of nonlinearity. That's, I think, really the main result.
I'm trying to get the physical message from this. I'm getting from this last slide that things are nicer than you might have expected.
Yes.
Is that right?
Yes.
Right at the beginning, you showed these pictures of diagnostics from various sorts of turbulence, which showed that things were extremely non-Gaussian.
Yes.
So that's presumably the effect of the opposite situation. That's very strong non-linearity. Have I got the right message on that?
Yes, but then whenever you see a highly complex system, I think all of us as scientists would say, well, can I extract some variables that put some order into this very complex system? And hopefully, maybe that's what this definition of these Ds actually does, because it's based on the symmetry. You know, the experiments alphas are based on symmetries of the system.
So what would that say? Tell me about this. You quoted the atmospheric boundary layer example. You said this diagnostic was very big, about 40, yeah. Is that right?
Yeah.
So how would that look in terms of the Ds?
Well, to be truthful, I don't know. It would be, if people have got the data, somebody can run it out and see. It basically, the very high flatness would mean it's an extremely highly developed turbulent flow. These are highly developed turbulent flows, although the Reynolds, this is Reynolds lambda 1000 for the Texas code, and I think the atmospheric boundary layer would be higher Reynolds lambda than that. So the question then is does this ordering and this depletion last if you sort of cranked up the Reynolds number even higher? That's the question. Now, is it some sort of analytic property of the system that we've just not proved, and I can't see how it could be true, or is it something observational that the system chooses to work in one regime but not in another, which is, I think, a slightly different thing. You know, if you've got regime 1 and regime 2, they're both theoretically possible. But if Navier-Stokes chooses to work in one but not the other, then we would want to know the reasons why. I'm not sure that answers your question, but
I'm still getting rather contradictory impressions from your first slide and your last slide, so I'm just trying to resolve them.
For the Euler equations, did all the DMs swap, or did just some of them?
now let me see. That's a good question. Offhand, I don't know. I think they all did.
Then they all swapped.
Because Bob has a paper on this in JFM that's come out very recently on Euler, and he has some plots where essentially the D's were like running on straight lines, and they essentially like converge together, and you've got a sort of crossover. So I suppose it's certainly more than one.
Oh, yeah. So when you have the bound on the sort of L infinity norm of the vorticity, that's pretty much, I mean, for 3D, I mean, that's quite essential to prove, I guess, global regularity of 3D Navier-Stokes. So I was just wondering, that's something that the theorists can look into, because that numerically it sort of tells the L infinity bound of the.
Yeah, if the Beam-Kato-Maida theorem would work for Navier-Stokes as much as Euler. And yes, the D infinity looks nice. It's sitting down there exactly at the bottom. But you do have to be, I mean, basically the statistics were solid from M is 1 to 9. The D is infinity. You've got to sort of extract from maxima, and you've always got to be careful extracting from maximum, because a maximum might fall between two grid points. So one, you know, the guys that know about these things are always cautious about what they claim about what D infinity is doing. But as careful as they've been, it looks as if it sort of all sits consistently at the bottom.
Any more questions? Well, if not, let's thank John and
Perfect
big
time.
everyone.